Thanks, Ben. That's really great, actually. Okay, next test on our list is misfire detection. So this is going to be something that I'm sure a lot of you are going to want to look into and start to understand. So we've got, again, 3 channels in use, slightly different order here. So we've got channel A, which is a time, it's 1 test lead, so we're looking at a crankshaft sensor in this case, and the detail of that. Then we've got a 60 amp clamp. So we're looking again at an injector signal here, just so we can see how the cylinders are operating. And then finally we're onto the common rail pressure sensor on channel C. In terms of how we're operating the system to run the test and capture our data, we need to start the scope, remember, but we're going to have the engine started but just running on idle. And we're going to see something like this, so something we've not seen yet. Crank channel there on channel A, really important signal to get used to. So we can look at the crank systems running, and the camshaft rail also output on there on channel B, which is our red signal. And then finally they've got a rail pressure sensor. So we're looking at the rail pressure there along, and you're seeing those nice, fairly even spikes running through. So that's it. So it's a very simple test in terms of connection, but I'm going to allow Ben, really, I'm going to pass you over to Ben, and he's going to run this system live on our digger here today, and he's going to deep dive into those signals and exactly how we start to understand what's going on. Over to you again, Ben.
Cool, thanks John. Okay, so misfire detection. So what we're going to look at is literally 3 signals. We're starting to get an idea about what might be causing a misfire. So there is a case study on our website which looks at how a particular issue with an excavator was caused, so it was poor performing. Customer wanted to spend lots and lots of money on replacing the hydraulic pumps. We sort of went in and said, do you know what, actually it might not be that. Do you want us to look at it first? We quickly identified that there was a problem with the engine side of the system, and then how can we determine where to go from there? So there was no fault codes, no warnings on the dash. What we were looking at then was, right, can we manipulate some of the signals we see and sort of show them in a way on Pico about what the engine's actually doing? One of those is with the crankshaft sensor. So in a couple of videos, obviously, we've sort of seen, and a lot on the forum, we talk about something called crank maths. Crank maths is really important with showing the analog output of the crankshaft sensor. So this is kind of how misfire detection works inside the ECU. It looks at the speed or the rate of change in the crankshaft sensor to determine how each cylinder is contributing to crankshaft speed. So we're going to use that. That maths channel is a built-in maths channel. However, with a lot of construction and plant machinery, they set their idle speed slightly higher than what the idle speed is in the crank sensor built-in maths channel. What we'll do is I'll quickly show you how to reform that and actually get a change in the output. So, other captures that we've already set up for. So I've got the crankshaft sensor on channel A. I have a cylinder identifier. Now that can be a number of different ways. In one of the guided tests, I think we're using the current clamp on the injector. If you can't get to the injector, camshaft sensor is another good one. If you can get to a camshaft sensor, great. If you can't get one of those, start to think slightly outside the box and maybe look at vibration from an injector pipe. You know, there's all sorts of different ways that we can try and determine how the engine is determining where it is in its 720 degrees cycle, so you can start to identify individual cylinders. Last but not least is the rail pressure sensor. Rail pressure can give you, we can, again, using the software, we can use some of the scaling features to identify how each injector changes the rail pressure after its injection event. A couple of things to consider is obviously if the pump and how many lobes are on the high pressure pump. So we'll obviously get a momentary increase in pressure because the piston in the pump has been forced up, obviously supplying the rail with more pressure and more fuel, more flow. And then obviously how that changes in relation to after each injection event. So we've got everything set up. We're going to load the guided test. Obviously loads more information in the guided test as well. We're just going to click, we're just going to minimize that for the time being. And we have our example waveform. Now this example actually has used the camshaft sensor as our cylinder identifier. Quick little tip, For the majority of machinery that I have seen, the cylinder 1 occurs after the double pulse on the camshaft sensor. So in this case, cylinder 1 fires round about here. Okay. What we're going to do is we're just actually going to get this machine started and start having a look at these signals. So we'll start the capture. Now, obviously, because the way this guided test has been written, it was actually taken using just 3 times-ton test leads. I've now put a current clamp on channel B. Now, that means our probe mismatch box is going to go, hold up, this doesn't match the original files. So what I'm going to do is I'm going to go, do you know what? I'm actually happy with how this is set up. So I'm just going to click Run with Found Probes. So it'll keep all of my settings as they are. All the time base is going to stay the same, but we will need just to alter channel B to make sure we can capture that injector signal. So Run with Found Probes. Obviously now we've gone to channel B, which is plus or minus 2 amps. I'm just going to put that up to plus or minus 20 amps, just so that we capture it. If it overranges, fine, we can always adjust it afterwards, but for the time being, we'll just carry on where we are. Right, channel C is our rail pressure sensor. And we can see that happening at the bottom. So what we'll do is we'll get it started and we'll see what the signals we've got. Okay, I'm just going to stop this briefly. I'm just going to switch the machine. No, we're going to leave the machine running. Hopefully you can still hear me all right. Just look at channel C for a second. There's an awful lot of noise present. Remember, the ground on a lot of machinery on this is quite noisy, so we're actually getting the effects of everything else that's connected to the ground coming through what on our fuel rail pressure sensor is quite a small signal. It doesn't change much. What I want to do is actually we just run this again. A couple of things we can do to help with that signal. Apply bandwidth limit. Bandwidth limit will reduce or take away any frequencies above 20 kilohertz. Now that is a hardware filter built in to the 4425A scope. Once it's on, you can't get it back. It's not like a low pass filter where we can switch it on and off. Once you've removed it, you can't get it back. Okay, so bear that in mind. I'm just going to take channel C and I'm going to reference it to the sensor ground. See how much that has changed that signal, how cleaner it is. So stop there, I'm just going to switch the engine off. Okay, so hopefully you could see the big change between the two signals when I had it connected to the chassis ground and then to the sensor ground. So bandwidth limit helps get rid of quite a lot of the interference from sort of the injector spikes, those frequencies that are occurring. But then actually using the sensor ground actually removes a lot more of that interference that we were seeing as well. The beauty of these scopes obviously is the floating impact aspect, so we can do that quite safely, and we couldn't do that necessarily with a common ground scope because there may be a potential difference between the ground on the sensor and the ground on the machine, which will then allow current to flow and be all sorts of mess. Right, let's have a look at these signals then. So we have our cylinder identifier by the current from the injector. We have our crankshaft sensor rolling away at the top there, and we have our fuel rail pressure sensor. Now, if I use the scaling function within PicoScope 7, and we just start increasing that more and more, start to see a bit of a pattern emerging. Yeah? So we can see now that actually, as an injector fires, we get a momentary drop in rail pressure. Injector fires, drops again, drops again. Yeah, can we sort of see that sort of going on? Again, we can actually increase that more. We can keep bumping the scaling up. So all I'm using here is the mouse wheel on my mouse. You can also do it within the software by going to display, and you see where we have scale there, and we can change the scale at that point. If you're using a touch screen, actually you can use the pinch and zoom function and actually use it directly on the axis. Okay, right, so how does that help us identify what each cylinder is doing? Going back to our crank maths channel now, so if we go to maths channels, you'll see here we have a crank A of 60 at idle. So this is a built-in maths channel. If we wanted to, we could count all the number of teeth up here, I know that there's 60. For a quick way of doing it, what we can do is add a measurement in. So we're going to do a falling edge count. Now this is 514. Obviously there's not 514 pulses in just one rotation. So we're going to actually measure between the rulers. So drag a ruler out to the missing gap. Let's move my ruler overview. So now I want to count the number of teeth that are in just that portion. Down on the measurement, click inside the lozenge, inside the window, and then click between rulers, and there we have it. So now I have 56 pulses. There's enough of a gap here to make up 4 pulses, which then gives us our 60. So crank A of 60 is the maths channel we are going to use. Let's just back out a little bit. So now we can start to see how channel A is graphed as an analog signal. So seeing how each time the injection event takes place or combustion takes place, how that affects the crankshaft speed. So all we're looking for here is consistency. So nice even pulses. We don't want anything dropping in and out too much. If we had an issue where there was an injector that was maybe blocked, we maybe see that one, crankshaft speed would drop instead of carrying on nice and even. 2, in the rail pressure sensor, actually we'd see, well, if pressure can't release, it's just going to stay static in the rail. So therefore, we'd actually get a slight build-up in pressure as opposed to it dropping after each injection event. Right, that was a very quick introduction to a lot of things. I hope some of it makes sense. Obviously, all of this stuff is available on the forum as well, where we talk about it in more detail. Obviously, the guided test has a lot more information as well as a reference, but there's loads of help out there. So if you ever get in a muddle, obviously contact us directly, or especially go to the forum, log in there, ask the question, and there will be myself or plenty of other technicians that will be able to help you. All right, thanks for watching. Back to you, John.
Thanks, Ben. I'm sure that introduction and explanation from Ben there really started to allow you to understand just how powerful PicoScope is when we're looking at issues around misfire. Okay, moving on. Possibly one of the most valuable things, and certainly something we get asked for more and more, is about understanding and looking at CAN networks. Feels like a huge subject, which of course it is, but actually with a few simple tips and tricks, you can really start to understand what's going on within a CAN network system. So in terms of connections, actually it's pretty simple. We're only using 2 test leads. It's channel A and channel B, and we're connecting in to the high and low CAN signals on the network. In terms of running the test, of course, we're going to have to start the oscilloscope software. Generally, we only need to switch the ignition on. You don't even need the engine running, but sometimes you do just need to start the engine just to kickstart the network. So that's our, and we're going to see something like this, and this will feel like a huge amount of data, but really is quite simple. So we've got our CAN high, which is our red measurement there, and our CAN low. So that's the blue and the red signals we see there. Really, really simple trick. If we use a maths channel, so A and B, I know Ben's shown you maths channels, and he's going to take you through this as well. What we expect to see when we take B from A is that we're going to see a really nice, clear, straight signal somewhere between 0 and 2 volts. So that's, once we've got that signal, we've got a nice, clear signal. We can then do serial decoding. And again, it's something we get asked all the time, you know, can we use PicoScope for decoding the signal? And more importantly, how do we do it? And yes, absolutely you can. So what you see there in the bottom, and I've just zoomed in a little bit just so you can see, and Ben's going to take you through this in detail, but yes, you can decode the CAN data and you'll get all that information there in a nice table form below, and you can also export that off the system if you need to. So really, really powerful tool and functionality within Pico, being able to view the CAN networks, but more importantly, being able to decode it. Right, I'm going to pass you over to Ben now. Actually, this one, would just like to give huge thanks to our friends at CNH. Ben was over at their training academy, and we did some videos which form part of this presentation. So huge thanks to them for that. And I'm now going to pass you over to a VT of Ben running through and looking at CAN networks over there a couple of weeks ago. Over to you.
Okay, so even with off-highway and any sort of agricultural equipment and construction, marine, we are all still using CAN bus. It's still very much a big part of the network structure within these machines. Some of these are even more complicated than most vehicles in the automotive world that are out there. So, networks are a big thing. One of the interesting features within these CAN bus networks is that they typically use something called J1939 protocol. Whilst we have our generalized automotive CAN, which is typically called J2534, J1939 is much more standardized. Now, that doesn't necessarily mean that every manufacturer uses the same bits of information, but there is a standard list that most of them will adhere to. Now, what that means is that we can do some clever stuff within our software. And that's mainly thanks to the software teams introducing a new decoder, which is the J1939 decoder. That actually breaks up a portion of the header of the packet of data and puts it into 3 columns. The columns are the priority, the PGN, the parameter group number, and the source address. I can't stress how important the source address is when it comes to fault finding. It may be that there are several gateways between your serial tool and the network that you are looking at. So how do you determine whether or not there's a problem with the network or a potential problem with the gateway? Well, this is where Pico can be really helpful, because by decoding that J1939 network, getting those source addresses, we can see which ECUs are online and which ones are not online. Now, I've picked quite a fairly basic one here. So underneath here, we actually have one of the knock sensors for the after treatment system. Now, I've literally just backpinned into the CAN high and CAN low signal on there, and then that will give us our information. So it will give us our raw voltages. We're not going to do anything massively different with how we capture. So there is a guided test for J1939 decoding, which we will load in. Once we have that loaded, it will give up our, our references, our known good, what we typically look at. It will give us our mass channel, and it will also give us our decoder. Now, most of the time, J1939 sits in 250 kilobaud. It is now moving to 500 kilobaud as well. So it may be that the decoder, which is defaulted in this case, in this guided test, to 250, it may be that if you are getting data that isn't decoding properly, you need just to change your settings to 500 kilobaud. Okay. So the guided test is already set up. It has done our settings for us. It has created the mass channel for us as well, so that A minus B. We're going to go ahead and we're going to go and start the scope capturing data. Now the ignition is on, so we should start to see our data coming in. And as you can see, the maths channel, obviously maths is only ever updated when we're in streaming, once it gets to the very end. And we can see our data and our list coming up. So I'm just going to stop the scope there for a second. We'll just go back a couple. Now, as we can see in our table, one thing to be aware of is the order that it goes into. If it's not in numerical order, just click the packet number and that will automatically put it into a list that is more reflective of what was going on. One of the key differences is how we've set this decoder up in this guided test is we put the format into decimal. Now, decimal is a different way of viewing it. Typically, it's usually hexadecimal, but you can usually find parameter group numbers listed in a decimal value. There's a fantastic website out there called isobus.net, and on there is actually a standardized list of all the PGNs that are potentially out there. Obviously, there will be proprietary ones on certain machinery. Of course, there will be. They have to protect some of their data. But for the most part, you can get a lot of this stuff. So the source addresses are also on there. Now, that's important when we come to look down the third column, which is our source address. And we can start to see that in this case, again, it's on the after treatment side, so it's a smaller network. There aren't as many ECUs on here. Now, being slightly sad and spending far too long looking at decoding J1939, I can already tell you that the source address 0 is for the engine controller number 1. So automatically I know we've got our engine ECU. 82 is actually one of our knock sensors, as is 87. And 41 is our after treatment ECU. So straight away I can see that there is 4 ECUs that are on this network. Now there is another little trick that we can do within the software, which is something called link files. Because we now have this standardized list that we can find, we can actually create a link file using the template from within PicoScope 7. We can create the link file externally, and when we apply it to the decode table in PS7, that will now change those values into a human readable form. What we're going to do right now is we're going to use a little bit of magic, and we're going to cut to myself talking through how to create link files and how to import them into PicoScope 7. Okay, so we're going to take a look at link files now. So what we're going to do is I've taken some J1939 decoded data, and obviously I've used the test, so let's set up the mesh channel for us and set up the decoder as well. Obviously, one of the things I mentioned in the video was that if you have an incident where the data is not decoded, you may need to change the baud rate. So to change the baud rate, if you click on this icon over here, you get the configuration set up for the J1939 decoder, and in there you have the baud rate. So it may be that you just need to change it to 500 kilobaud. A real quick, easy way to check what your baud rate is, if you go into a packet, so let's take this example here, and all we're going to do is take 2 time rulers and measure one of the smallest pulses. Now this can either be in any direction, it doesn't matter, so just literally the smallest gap. So here obviously we can get a bit closer as well, but you can see there that that's pretty much in the 250 kilobaud mark. So yeah, if I wanted to zoom in a bit and get that even closer, I'll see on the 2 edges, there we go. So 250 kilohertz is equivalent to 250 kilobaud. Okay, right, let's zoom all the way back out again. So providing that we have all of our decoded data listed underneath. Now, as I said in the video, I have mentioned that this decoder is set up into decimal. The reason being, obviously, is that PGNs, they typically come in a decimal format, and it also means the source address will be in a decimal format as well. The website I mentioned was the isobus.net website. So here we have the website. It's automatically, I've just clicked on addresses, and here we have all of the predetermined isobus source address IDs. These are typically standardized, and what you'll find is that there are different industry groups which obviously have different, they do change some of the source addresses depending on which industry you're in, so be mindful of that. If you just click on the different ones, they will just bring the ones that are different. So for this example, these IDs, these source addresses are similar to ones that exist in other industries, but obviously they have different names. Okay, so all we're really going to get interested in to start with is the global, so applies to all. Straight away you can see that there are some very obvious ones at the top. So what we're going to do is we're going to take a few of these, maybe we'll just take 2 or 3, and you just give you the idea about how to set the link file up. So if we go back to PicoScope, here we've got 0, there's 3, there's 15, so we'll take those 3 as the first ones that we're just going to apply a link file to. So if you click data to text and then create a template, it's going to ask you to set that template somewhere. So all I'm going to do is I'm just going to put it on the desktop. So we'll call that J1939 source address. And I'm just going to put decimal at the end, just in case if you were working with other templates, you want to make sure you're working with the right one. So decimal just means keep everything in decimal format. Click save. Right, okay, now what we need to do is open up that file. So if I just go to our desktop, all I'm going to do is open up this Excel sheet. So it should hopefully open up in Excel, and we should be able to start editing this template. Let's drag this over. Okay, so now we should be able to make some relationships with the decode table and the headers in this link file. So the ones that we're really interested in are things like the source address and the PGN. So we're just going to start with our source addresses just because in my experience they are the most useful one. So all this is a lookup table. It's nothing different. It's nothing more special than that. So all I want to do is I want to say, right, if my source address is 0, I want the software to return the description as, again, if we just quickly nip back to our isobus directory, engine #1. Engine #1. Okay? Very, very simple like that. One of the other ones we had was 3, so we're going to use transmission number 1 as well. So transmission #1. And I think there was 15 as well, wasn't it? Let's just quickly jump back in. Yeah, 15. Okay. 15 is retarder engine compression braking. Okay. So back to our link file. So 15. My mind's gone blank already. Retarder engine. Okay, we'll just keep those as those 3 for a second. Right. Make sure you save it. And then we're going to close the software down. Now, the only reason being is that I have found in some instances it doesn't always update. If you make a change, save it, you have to keep going in and out of the link file. It's just more of a process for me. So I'm just going to close the Excel sheet for a second. I'm going to go back to PicoScope. We're going to go data to text, and I'm going to click open. So hopefully it will find our J1939 source address. Click OK. We'll see you work through all the different decoding sections, and then there we have it. So we've changed 0 into engine, 3 into transmission, and 15 into retarder for engine. So you can now start to see how that can be useful if you're trying to trace down ECUs that are potentially offline, or like I said in the video, if there are particular gateways. Obviously the benefit of Pico here in this instance is that you can go anywhere. All we're doing here is actually just hopping into the CAN high and CAN low, and then obviously decoding that data from there. You might not be able to do that with your scan tool if there's not a serial port on every network. So this is just a quick way of just determining whether or not you have actually got traffic. Using the J1939 decoder, we can split that header up into the 3 columns, and then you can use the source address here to actually determine which ECUs you have present on that network and which ones aren't. The same thing applies with the PGNs. Obviously on the isobus website there is actually a PGN section, and again you can do exactly the same format with your link file. All you need to fill in is the number that you're going to use. So one that's quite common is 61444, which is for electronic engine controller number 1. So if you have this number, you put it in your lookup file. Obviously you can change the description to engine controller 1, and then in your lookup table you will actually have, so this very top one, for example, 61444 would now say engine controller number 1. All right, I hope that helps. If there's any sticky points with that, or if you want to ever look for some more information, don't forget under the support material there is actually our A to Z of PicoScope. In there is a section on J1939 serial decoding, which will take you to a link on our website. Within that website there is an animated GIF which can also talk you through how to set the decoder up, and also a bit about using the link file and how you can change the values into readable data. Okay, I hope that helps, and thanks for watching.
Thanks again, Ben. That's great. And I know that will be really valuable to you guys, understanding how you can look into CAN networks. Okay, so just kind of tidying up on the end of this section of our presentation. Just a quick recap in terms of understanding waveforms. So we've got those 3 things: that connect, that run, and that read. What information is available to you? Just to recap, guided tests, really, really valuable. So within that, you're going to get connection, how you perform the test, example waveforms, so what you would expect to see when you've captured that data, as well as notes around the waveform, so why is the waveform the shape that it is, and also moving on to further advice. So really, really valuable. Use the guided tests. as much as you can. And yes, we've got specific off-highway guided tests, but some of the automotive ones, particularly around, engine systems, are going to be equally valuable to you as well. Waveform library. Ben will have touched upon it earlier, didn't he, in his software introduction. Being able to have access, to a good known waveform on a system is really, really valuable. Again, we understand a lot of what you see in there is automotive, but you can look in there for off-highway manufacturers. They're all contained, so quite often it will just help you out, in an understanding of how that system works. And then, building your own knowledge. It's not all sadly contained within our software. We put in as much as we do, and as you can see, we're continuing developing that information. But watching videos, we're going to do more and more presentations for the off-highway market, so make sure to follow us on YouTube. Come back here and we'll continue to add more and more information. Case studies on the website, so we have a whole case study section. And again, a lot of the great work that Ben's doing is around case studies, on off-highway equipment. So keep an eye on that. It'll really give you an insight in applying PicoScope to diagnostic problems. It's going to really give you a nice highlight there. And also, of course, the forum. So, we touched upon it a little bit earlier, but the forum there, get involved. There's an off-highway section. Some of the smaller case studies, people are sharing information and problems on there as well. So really keep a good eye on there, because it's a way to build your knowledge. And finally, training. There are obviously off-highway training providers. Amping your own understanding and use of diagnostic equipment, including oscilloscopes, is really going to build your knowledge. And what's it about? At the end of the day, it's about you being more sure of the diagnostic process. So we go right to the beginning. If you remember that opening slide that I had there about what you do today is going to make it easier for you to build your understanding for the future. So just bear that in mind when looking at a diagnostic process, and particularly working with an oscilloscope.